Welcome, everybody. We are delighted to have Nuno Santos with us today. He studied physics in Lisbon, and in 2002, he did his PhD in Geneva, in Switzerland, actually. Later on, he then went to Porto, where he is since 2012, a researcher with the status of a full professor, as I understood it, at the Institute of Astrophysics and Space Science. And this institute is also an institute that he founded together with other members. Since 2015, he's an assistant professor at the Department of Physics and Astronomy, also in Porto. So he has these two roles. And he is very productive. He received several prizes and many grants, including an ERC. His interests are very broad, ranging from planet detection and characterization to stellar astrophysics and the star-planet connections. And this last topic that I mentioned is also something that he will talk about today. So for the audience, please switch off your cameras, and Nuno, the screen is yours.
Okay, thank you very much, Caroline, for the introduction. And thank you very much for inviting me to give this talk. It's really a pleasure. I think I'm also going to switch off my camera just to be sure that I don't have any bandwidth problems, but I will connect it back in the end. So let me put this in full screen mode. So I hope you can see everything well. Let me know if not. So I'm going to give you a short talk, let's say, about the importance of knowing the stars when we want to know the planets. And this work is done, I mean, I'm going to present mostly some results that were done in collaboration with my colleagues, Vardan Adibekian, Sergio Souza, and Elisa Delgado Mena, but also others that work with me in Porto or other collaborators, including actually Caroline. So yes, so basically I'm going first of all to give you actually a rather long introduction about why study stars with planets is so relevant. And then I'm going to move to the particular case of the star-planet chemical link, with a short overview of what we know concerning this link for stars that host giant planets, and then moving to the more exciting, let's say, star-planet connection for low mass or small radius planets. And in particular, I will show you some later results we have about the connection between stellar chemistry and planet composition. So why is studying stars so important when we are in the exoplanet field? There is actually a number of reasons for it. I'm not sure if you see very well this video or not. This is the transit of Venus as seen from Earth or from Sol, I think. And you see the sun, you see the small Venus disk passing in front of the sun. And what we see here is that the sun is actually not, a spherical uniform ball. It has a lot of activity stuff happening there. And indeed, all this activity, actually, it perturbs a lot our capacity to detect planets. So understanding stellar activity and all the noise and signals, let's say, that stars produce is actually an important aspect in exoplanet research. For example, this is a simulation that was done by Xavier Dumousk a few years ago, where you see a spotted star with the spots appearing and disappearing. And on the right plot, you see the radial velocity that you measure as a function of time. So this little red dot going up and down, you see that it oscillates more or less up and down by 1 meter per second, give or take. And so this is the kind of noise that stellar activity does on a solar type star. Now, when you compare this amplitude of the signal that the star produces with the 10 centimeter per second needed to detect an Earth-like planet, you understand that there may be a problem. So we really need to understand stellar activity if you want to find planets like our Earth. Now, to tackle this problem, this is actually a very difficult issue and subject of many research these days. There have been many different approaches. So people try to use, to diagnose and correct for these spurious stellar signals using activity proxies measured in the spectra or complementary photometry, for example. There's also approaches where people try to use specific spectral lines or spectral regions that are more or less sensitive to stellar activity. There's also physically motivated models. Probably few of you heard about SOAP. It's one of the models that we have been using, but they are usually also oversimplistic in the physics, so it's not necessarily, they're not complete. They cannot really model what is happening with all the necessary detail. And most lately, there have been a number of works trying to use mathematical models, including not only, but very often Gaussian processes to actually model out the signal produced by stellar activity. And in the bottom plot here, I show you this is basically the radial velocity time series of the Proxima Centauri that allowed us to confirm the rocky one Earth mass planet orbiting this star with espresso. And actually the curve you see here is a Gaussian process fit that allowed us to subtract the contribution of stellar activity. And actually this was the dominant source of the signal. So without this kind of correction, we could not have measured the mass and detected this small planet orbiting Proxima Centauri. Now, stellar activity is also a big problem when we deal with exoplanet atmosphere detections. And here I show you just one example. On the right plot, you see, so the points are the transmission spectrum that were obtained of LHS 1140b and by Edwards et al. Recently. And on the top panel, you see the blue line is a model trying to model the observer data using a model transmission spectra that assumes that there is water in the atmosphere of this planet. This is a small planet, so water is becoming a relevant thing here. But on the bottom panel, we see that we can actually also more or less model this transmission spectrum if we assume that actually the planet was crossing in front of spots or faculae in the surface of the star. So this shows you that, I mean, stellar activity, if we don't manage to deal with it, we actually will not be able to understand exactly what we are observing when detecting exoplanet atmospheres. And finally, I mean, in transit photometry, stellar activity is also extremely important, in particular when you have, for example, the crossing of the planet in front of spots, because when this happens, I mean, in the transit light curve, you'll see these bumps that are signed here as red. They are flagged here in red. And actually, when you see them very well, you can maybe dream about correcting for them, but sometimes the effect is very small. And the net result is that you will get a wrong radius for the planet, for example. And so all this is extremely relevant. And the understanding of stellar activity is indeed one of the major issues that are now being investigated and that somehow connect the stars and the planets, right? So the second reason why we should understand stars is because very often the stellar parameters that we derive, the planet parameters that we derive, they do depend directly on the planet parameters, on the stellar parameters, sorry. So for example, to get the planet mass, the radius, and the mean density, we need to know the stellar mass and radius. This is inherent to the methods that are used to detect and measure the properties of the planets, namely radial velocities and transit photometry. Also, to get the system's age, the only way that I can think of is to look at the stellar age or try to derive the stellar age. And of course, the stellar properties will strongly influence the potential of habitability of a planet. Just to give one example, so when we measure a planet with the transit photometry, we can get orbital parameters, but also we can get actually the planet to star radius ratio. So we need the stellar radius to know the planet ratio. From the radial velocities, we get also orbital parameters, and we derive the planet mass, but only if the stellar mass is known. And so if we want to get the mean density of the planet, and so its composition through models, we really need to know stellar mass and radius with very high accuracy. And so this is again one example of where studying the stars with planets is so relevant. Now, finally, and this will be what I will speak about in the rest of my talk, there's actually a number of observed correlations between planet and stellar properties that give us a lot of information about the formation, evolution, and even the composition of the planets themselves. For example, there are relations between planet occurrence and stellar metallicity, or even stellar mass, that tell us about planet formation processes, or about the frequency of planets in our galaxy. And also there are now growing hints that there may be a correlation between several planet properties and stellar properties that condition, for example, the composition of the planet or even planet architecture. Now let's look at this star-planet chemical link in a bit more detail. And I will start by the giant planets. They are a little bit less sexy than the lower mass rocky planets, but they still hide a lot of interesting information about how planetary systems come to be. And so by giant planets, let me just say, so this is a plot, a mass period diagram of known planets. I think last week it was taken, I believe, from exoplanet.eu database. And by giant planets, I mean planets that have masses more or less above 30 to 50 times the mass of the Earth. So I will focus now for a while in this yellow region in the plot. So planets that are in principle gas giants, or that have a very strong contribution from gas. Now, one of the first results, just very soon after the first exoplanet discoveries, was actually that when you look at the metallicity distribution of stars with giant planets, and you correct it for your observational bias, so the metallicity distribution of your sample, you can plot the frequency of planets as a function of stellar metallicity. And you realize that actually, as you go towards higher metallicity stars, you can start to get more and more, you find more and more planets, giant planets. This result was obtained, as I said, very soon after the first detections of exoplanets. And there are a number of papers, discussing this since then. And actually, this result has been often seen as strongly supporting the giant planet formation mechanism through core accretion models. And in a very naive or very simple way, what is behind is that if you have more metals in the disk, you can grow the core faster before the disk dissipates, and so you can form giant planets more easily than you would do if the disk is metal poor. And we are assuming, of course, the metallicity of the disk is correlated with metallicity of the star, because they all came out from the same cloud of gas and dust in the interstellar medium. Now, this is very, very clear, this correlation, but there's actually a number of open questions in all this. And one of them is, what is exactly the dependence between the frequency of planets and stellar metallicity? So we're talking about giant planets only here. And there are actually contradictory results here. So there's, some people, including us, have proposed that maybe there's actually two different regimes here. There's let's say, a regime for higher metallicities where there's an increase in the planet's frequency as we go towards higher metallicities, but also a long flat tail towards lower metallicities in this distribution. Other people have proposed that no, maybe this is just one simple function. We have actually explored this in this paper by Mortier et al. In 2014, and we realized back then that we needed, I don't remember the number by heart, but I think it was like 5,000 giant planets to be able to distinguish statistically one case from the other. So the answer is not yet there. So we don't really know if this represents two different populations of planets or one single population. But more recently, we looked into this with a bit more detail. And we realized that when we plot the number of planets, so this is just simple frequency plot, so the number of planets as a function of their mass, only including giant planets from 1 Jupiter mass up to 15 times the mass of Jupiter, we realized that there's actually some sort of a discontinuity in this distribution around 4 to 5 times the mass of Jupiter. So we decided to investigate this a little bit further. And what we realized as well is that if you cut the sample in lower mass giant planets and higher mass giant planets, meaning that lower mass are giant planets with masses below 4 times the mass of Jupiter, and high mass giant planets are giant planets with masses above 4 times the mass of Jupiter, the two metallicity distributions are statistically significantly different. And actually, the higher mass Jovian planets, they tend to orbit more metal-poor stars. I mean, it's not entirely clear if this is the cause for this. There's a number of details. I'm not going to enter into all of them. But actually, we could be seeing the signature that the higher mass planets that we are observing could be formed by another process other than core accretion. Maybe disk instability related. I don't know. I'm not expert in it, but it's evidence that should be taken into account. Anyway, so this is what I wanted to tell you a little bit about the correlation, let's say, between stellar metallicity and giant planet properties. It's just basically to tell you that although it's not so exciting to look at giant planets these days, there's actually a lot to understand and a lot of questions that do deserve to be tackled. But let me now move to the lower mass planets. So I've shown you before that when you look at the metallicity distribution of stars with giant planets, they are on average very metal rich when compared to the Planet Search samples. And now what happens if you go to the lower mass planets? So by lower mass planets here, I mean planets that have masses below, give or take, 30 times the mass of the Earth. So they are Neptune-like planets or super Earths. A few of them, they are really rocky and low mass planets like our Earth, but most of them are not yet in that regime. Now, when you look here at the metallicity distribution of the stars that have low mass planets, you actually find something a bit different from what you see when you look at the same thing for stars that host giant planets only. And here on the left plot, you see in orange, this is the metallicity distribution for stars that host giant planets. And in yellow and in gray, you see the stars, the same distribution for stars that host low mass planets and the metallicity distribution of stars in the solar neighborhood. And what you see here, so on the right panel, it's maybe even easier to see that. This is the cumulative fractions of the three histograms. And what you see is actually that while stars with giant planets do show a very clear metallicity enhancement, the stars that host low mass planets, they do not show that. So their metallicity distribution is just the same as you see in the stars in the solar neighborhood. And this is very, very interesting because it means that there's something in the models of planet formation that should explain why there is this dichotomy. And one of the approaches is that, okay, I mean, to form lower mass planets, you actually don't need so much metals. And so you can form them around stars with a much wider range of metallicity. And actually, it could actually play the other way around. If you have too many metals, you start forming a lot of giant planets and you actually transform the low mass planets into big ones. And so you could have the opposite correlation, or you could even maybe expect the opposite correlation. That's not necessarily what you see, but okay, there's this clear dichotomy between the two that can be explained in very simple terms by this mechanism. Now, just to say that this correlation was also found when this lack of, or this difference between giant planets hosts and low mass planet hosts was also found on Kepler data. So the previous results that I've shown you were mostly based on radial velocities, but also transit photometry results. But here, just using the Kepler data in 2012, Lars Bukave has shown, he has sort of confirmed what was suspected before, that indeed the stars that have giant planets, so here the red histogram, they tend to be more metal rich, but the stars that have low radius, small planets, they actually peak at around solar metallicity, which is basically the metallicity distribution of solar neighborhood stars. I mean, there's also a lot of debate around this, and there's a number of papers that I'm mentioning here. You can look for them later if you want. But anyway, this is a bit the overview of the situation. Now, what is interesting, though, is that we are now finding evidence as well that it's not only a question of frequency of planets depending on the chemical composition, or in particular the metal content of the star, but also the composition of the planets themselves that can be related with the composition of the star. And now to go into that, so now you know that stars that we observe in the solar neighborhood, they have different galactic populations. They come from different galactic populations, and they have different metallicities. So in this plot I show you, this is the alpha element over iron as a function of iron content of the stars in the solar neighborhood. And actually the different galactic components, they behave differently, or they position differently in this plot. You see thick disk stars, they typically occupy this region up here. They are alpha element enhanced when compared to iron. The sun is here at 0, 0, so I didn't put the position of the sun here, but it's 0, 0. So the sun is a typical thin disk star. There's also this bunch of stars here that there's a debate on what is the origin of these objects, but they are some sort of metal-rich thick disk objects. Maybe it's not clear, but there's this bunch of stars here which are actually interesting from the galactic chemical evolution point of view. But overall, you see that the alpha over iron abundances of these stars, they spread about a factor of 2 in abundances. And so one question that we could ask is, do these stars here have or are able to produce planets with the same composition as these stars here? I mean, you could expect that that's not the case, because if the stars had the difficult abundance ratios, then the planets will probably end up having also different abundance ratios. Now, let's look at what we can expect first. Now, this is a result from Asplund et al., where we plotted, this is the photospheric minus meteoritic abundance of the elements as a function of atomic number. So the difference between the chemical composition we observe on the sun and in meteorites. And in this plot, you see that basically the difference, the average difference is 0. I mean, most of the abundances, most of the elements seem to have the same abundance relative to I don't know exactly what was the reference here, but relative to each other than we observe in the sun. Of course, let's exclude here hydrogen and helium, because the sun is a big ball of hydrogen and helium, basically, right? So if meteorites don't have so much of it. So if we take out hydrogen and helium, we see from this plot that the abundances of all the elements, they are more or less the same in the sun and the meteorites. Now, actually, we know from a number of studies that both Earth, Venus, Mars, and the meteorites seem to have more or less solar relative abundances of iron, magnesium, and silicon. And so the question is, can we actually use iron, carbon, oxygen, magnesium, and silicon abundances in the star to predict the composition of the rocky planets that we observe? And so Mercury is oddball in this respect. We don't know exactly why, probably because of giant impact, but I don't want to enter into this right now. But anyway, so this is the global trend. So the question is, can we actually use these facts to predict the chemical composition of the planets once we know the chemical composition of the star? And this would be very helpful, because when you do models of planet interior, if you could get this prior information from the star, that would definitely be very, very relevant. Now, to do this, back in 2015, and actually following an idea by Christophe Mordazzini, we did a very simple stoichiometric model where we can compute actually, I mean, a number of things, but the two most important ones, I would say, is what we call the iron mass fraction, this F iron here, and the water mass fraction of the planet building blocks based on input measured stellar abundance of carbon, oxygen, silicon, magnesium, and iron. So it's really a very simple stoichiometric model, assuming that the planet is basically made of just of iron in the core, and then or that the planet building blocks are basically made of iron and some silicates or mantle-like composition molecules. And so once we apply this model, we can try to see if what we see is what we expect, right? We did that actually. We looked back then. There were a number of low mass planets that had been discovered already. And here I show you this is the planet radius as a function of planet mass. So the typical mass radius diagram. We see here these lines are lines of the locus of planets with different chemical composition. And we see that there was this bunch of planets here that were very close to the Earth composition line. And so our question back then was, do the stars that host these planets have chemical composition similar to the sun? Or can we, from our stoichiometric model, conclude that we expect these planets to have also the composition similar to the one of the Earth? So an iron mass fraction, let's call it like that, similar to the mass of the Earth. Of course, we are always talking about the chemical composition of the planet building blocks, because planet formation is a wild thing, right? So, but at least if the chemical composition of the planet building blocks could fit into the position of these planets in this diagram. So we actually back then we managed so we selected these rocky planets here, and we asked the question: so can we predict the composition based on stellar chemistry? And actually, we measured, we obtained a spectra for 3 of these planets: Kepler 10, Kepler 93, and Corot 7. And we applied our stoichiometric model, and we got a bunch of things, but the only line I want you to look at now is the last one. So the iron mass fraction, which if a planet is composed of this and is fully differentiated, I think can be seen as the core mass fraction as well. And the results have shown that basically the numbers we obtained, it's basically 32%, 35%, and 27, 28%, are basically within error bars, more or less the same as we obtained for the sun. So this seems to corroborate the idea that there is a correlation between the chemical composition of the star and the expected composition of the planets in this mass radius diagram. Now, the interesting thing, though, was that although for these 2 cases, we would expect indeed values very close to the solar one, and at least within the error bars, for Kepler 10, the value was a bit lower. And we also realized when we look at the plot that Kepler 10, that has actually 2 planets, is a bit alpha enhanced. And also its planets seem to be slightly lower density than expected. So they are a little bit above the Earth composition line. So this sort of tells us, okay, maybe this is just, errors and we should not believe in one point, but it encourages us at least to continue and pursue this kind of analysis. Now, the first thing we did was, because we didn't have more interesting planet candidates back then, was to try to see, okay, let's first assume this is a good approach and that we can actually predict the planet composition based on the stellar composition. So what would be the composition of planets in our galaxy? So what we did was we took a sample of solar neighborhood stars that have very good HARPS spectra. Where there were actually 371 stars with very reliable parameters and chemical abundance of carbon, oxygen, magnesium, silicon, and iron. And so we applied our stoichiometric model we used actually stellar parameters and that are homogeneously taken from our SweetCat catalog. So SweetCat, just for publicity, is a catalog of stellar parameters for stars with planets that we are maintaining here in Porto. It's open source, everybody can and I think should use it. We really try to use to have homogeneous data sets so that all analyses are done in the most homogeneous and unbiased way. And so I think it's a rich catalog, especially because of that. There's a new version that is coming out in the next few months, also a nicer interface with some Python scripts for you to query around and cross-check with the exoplanet.eu and exoplanet.org databases. But anyway, I let you explore this if you think it's useful for you. But anyway, we took all this from SweetCat and we computed the expected abundance of the planet building blocks and maybe of the planets that could be produced around stars in different galactic populations. And we found three different things that are, I think, quite interesting. So on the left, you see this is the iron mass fraction of our stars and of stars in the different galactic populations. So what we see is that thick disk stars, so these white histogram things, they are all, so they should produce planet building blocks that have the same iron mass fraction as we see on the sun and as we see on the Earth. So this is what we expect more or less. But the funny thing is that for thick disk stars that are alpha element enhanced, we do expect them to have lower iron mass fractions. And so if the planets are built out of these planet building blocks and then they are differentiated, you expect these planets that orbit at least the rocky planets that orbit these thick disk stars to have smaller cores and bigger mantles, putting it in simple. Also, on the right, you have the same histogram, but for the water mass fraction that we can also derive. Now, water and water delivery to planets is a very complex thing. And so we should see this as the water content of the planet building blocks, not necessarily of the planets. So, but it's maybe a good proxy for the available water in the planet formation disk. And what we see is that, again, so what we expect for thin disk stars like the sun is that they occupy a region here where the water mass fraction should be around 50 to 60%, let's say. But thick disk stars, they should have disks with much higher water content, let's say, than the thin disk star. So in principle, a planet formed around the thick disk star could have more water, or the reservoir for water in the disk could be bigger than the one we see around a star that is from the thin disk of our galaxy. Although, as I said, water, we should be careful about it. Anyway, so back then, as I told you, so we had 3 planets that we studied, or 3 stars with planets that we studied. We did, we tried to understand what was the composition of planets or planet building blocks in the galaxy, assuming our model was correct. And of course, from this left plot, we see that, we could actually expect thick disk stars to have a quite different chemical composition. The planets forming around thick disk stars could have a quite different chemical composition when compared to the planets formed around the thin disk stars that we like our sun. And so I know time passed, there were more planets found, and more recently, with my colleague Vardan, we decided to look into this again, and so we decided first to select planets that have mass and radius determinations at better than 30% precision or accuracy, and so we plotted them in this mass radius diagram. Now you see these gray points here, you see the red points up there, and there's this valley thing here that it's quite well known. So basically the idea is that the planets up here, they have a quite large envelope of gas around it. So we are not actually seeing the radius of the, let's say, rocky part of the planet. But the planets down here, they are mostly rocky, or they are expected to be mostly rocky in composition. And so we wondered, okay, what happens if we just select these ones? So let's just select rocky-like planets. and then let's apply our stoichiometric model. So to do this, we derived abundances of iron, of course, but also of carbon, oxygen, magnesium, and silicon for all these for all these planets. And then from these, applying our stoichiometric model, we derived the iron mass fraction for all these planets, the expected, or at least the iron mass fraction, as I said, for the planet building blocks, the expected one from the stellar composition. And this is the first thing we found. So in this plot, I show you this is the density of the planet normalized by the density of a rocky composition planet of the same mass, okay? And this we plot as a function of the expected iron mass fraction of the planet building blocks as derived using the stellar composition. And we see from this plot that there is a quite nice correlation here. Now, the funny thing here is that this planet down here, this TOI 561, is a planet orbiting a thick disk star in our galaxy. So indeed, it seems to be, there seems to exist a good relation between the composition or the density of our planets as normalized by the expected density of an Earth-like planet in composition of the same mass, as I said, and the chemical composition as expected by our simple stoichiometric model. Now, it's also clear from this plot that there's this bunch of planets here that seem to be a bit too high. I don't know exactly what this means, but these seem to be some kind of super Mercuries, so they are too dense. They all orbit metal-rich stars. I mean, stars metal-rich, they produce planets on this side of the plot. Metal-rich, I mean iron-rich stars. And so the explanation for these super Mercury-like planets is not very clear. We thought about giant impacts. I don't think this can really explain it, because if there were giant impacts, there wouldn't be a reason to be a gap between these two populations of planets here. This should be more a continuum thing. And so the only explanation we have is something that actually came from a recent paper by Aguichin et al., where the formation of planets near rock lines is invoked to explain the possibility that planets can have, after their formation, without giant impacts, bigger or higher core to mantle ratios, like Mercury. And probably a combination of the two could maybe explain all this. I don't know, but anyway, this is under debate. Okay, this is actually a paper that is not yet published. It's almost accepted, but it's not yet published. Anyway, the second thing we did was actually asking Caroline, and so Caroline computed the iron mass fraction of the planets based only on the mass and radius of the planet. So only on the knowledge we have about the mass and the radius of the planet, without any knowledge on the star. And we compared it with what we observe based on our stoichiometric model. So what would be the expected chemical composition of the planet based on the stellar abundances? So these are two independent measurements of the same thing, let's say, or more or less the same quantity. And what we see again is that there is indeed a good correlation between the two. So it seems that the composition of the planet, as derived from the mass and radius relation, is in agreement, let's say, is correlating with the one that we observe or that we expect from the chemical composition of the star. And however, there's one very important caveat that you see from this plot very clearly, is that the spread in this y-axis is much bigger than the spread in the x-axis. So it seems that let's say the difference in the chemical composition of the stars that we see in the solar neighborhood can actually produce a much larger spread in the chemical composition of the planets that we observe in practice. So there is a correlation between the two, but it's not necessarily a one-to-one correlation. And this is also, of course, a very interesting aspect. But overall, these results seem to confirm that indeed the chemical composition of the star can be used to infer somehow the chemical composition of the planets, at least to a certain degree. So this is basically what I prepared for the seminar today. So in brief, I think or at least I hope I convinced you that the study of stars is indeed providing very important clues for exoplanetology, including about the planet formation processes, planet frequency in the galaxy, and the planet composition and diversity. And that most of all, that the study of the stars with planets is indeed fundamental, both for present and future efforts in exoplanet research. And so thank you very much for your attention. And I'm open
Thank you.
questions.
Thanks a lot, Nuno, for this very nice presentation. Maybe everybody, if you have a question, you can raise your hands. You can even type your question in the chat if you want, but I think it's easiest to just ask the question in person. And while people are thinking about their questions, I already have one. I was wondering, in your introduction, you said that there is not necessarily this correlation with metallicity and occurrence of planets for the low mass planets. I think, yes, exactly this plot. And I was wondering if that tells us something about the efficiency of planet formation. So the formation of low mass planets doesn't seem to be affected so much by the available metallicity. And thus, does it mean that maybe it's not so efficient to produce planets? There's always a lot of material still sitting around that can be assembled to form these low mass planets, and there's enough time to form them without such that they don't accrete gas. So essentially the question is, does it tell us something about the efficiency of planet formation?
I think this sort of corroborates what is the result for the giant planets, in the sense that if planets are formed by binary accretion somehow, you do expect that the more mass you have, more mass of solids you have in the disk, the faster you grow them, right? And so the thing is that for the low mass planets, you can still form them even if you don't have huge quantities of solids, while for giant planets, you need to grow the cores very quickly before the gas dissipates, or else you end up only with a small planet. There is, however, let me just change the slide. So I think it's this paper by Zhu et al. They point out to something that is quite interesting, is that probably, and there are actually hints of that, probably there is still a correlation between the frequency of low mass planets and the stellar composition. However, it's so easy to form low mass planets that you always end up having low mass planets even if you have low metallicity. And so you probably have more low mass planets in higher metallicity stars, but you don't see it very easily in the plots. It's just because every star has low mass planets somehow, even if it's just one smaller one, So it's still not fully clear. I mean, what is the real correlation for the lower mass planets? But it's at least not as strong as the one we see for the giant planets. And I would say that both of them converge towards the traditional core accretion scenario for planet formation, let's say.
Okay, thank you. I let other people also ask questions as I have more. Ravid, you were raising your hand first.
Yeah, so thanks for the really great talk. So I have two quick questions. So the first one is, when you see the correlation with the with the iron abundance in the stars, I was wondering what how diverse was the stars in your sample, because it depends what type of the star, right, you're having. So I wanted to hear what you, just the statistics of the sample, and whether you think it's going to be like that for all stellar types, or is it really relevant only for sun-like stars? Yes.
So when you mean, I'm showing a hidden slide here. I'm not sure if it answers your question, but so when you mean diversity of stars, you mean diversity in terms of a mass. Okay,
Yes.
so this plot does not answer you. So the diversity in mass, so these are basically solar-like stars. So let's say between 0.8 and 1.2 solar masses, give or take. However, this correlation, especially for the giant planets, has also been seen for the M dwarfs. And actually, I think there are not many giant planets around M dwarfs.
Right.
M dwarfs tend to lack giant planets. But still, we could find a correlation for M dwarfs. So it seems to hold for the lower mass stars as well.
Okay, and then my second question is, you know, a while ago there was also the issue of you know, pollution of the stellar envelope, and also the, you know, different generation of planets, and maybe there are some planets that fall into the star, and this is why you have signature of you know, heavier elements. Can you tell me what's your take off on that? I mean, do you think it's still a valuable explanation for this correlation?
My personal feeling is that it can explain part of the spread, but it cannot explain the full thing. And the main reason is, I think one of the first arguments that was used to support that is that if you plot the chemical composition of the stars with planets as a function of the convective envelope mass of the star, so if there's infall of material, it should mix up with the convective envelope of the star, you see no trend there. So the upper envelope of that relation is basically constant. And if you would put a given amount, the same amount of metals into the convective envelope, you would see clearly a trend. And so this sort of suggests that this is not the main mechanism. And I think that as the knowledge went forward, I think that the idea that this is really a signature of the processes of planet formation is the one that is that convinced the community.
Thanks.
You're welcome.
Haiyang was next.
Yes, thanks. Very nice talk. So actually, I also have a couple of questions. First on this, actually, Nuno, when you say low mass planet, what do you exactly mean? Do you include like the planets with the mass less than 2 Earth mass, for example?
No.
Or have you? Yeah.
No.
Especially the next.
It's less than. I think I don't remember exactly what was the limit used in that plot, but I think it was 30 times the mass of the Earth. So when I mean low mass, I mean Neptune's, Super Earth, and Earth altogether.
Okay, altogether. Okay.
Yes.
So for your in the next 2 slides, the distribution with radius less than 4 Earth radius. The next slide. If you can. Yeah. So have you considered to only plot the planet with radius less than 2 Earth radii and see if how the distribution would be compared to this? So
yes, yeah, that's a very good question. I think a couple of years ago we did this, and I don't remember seeing any specific thing there. But I will. To be honest, I will check again. You know, numbers are growing. So now the problem very often is that, you know, the Kepler sample is very tricky because the stars are very faint. And for most of the cases, we don't really have reliable abundances for the stars. We don't have the masses for the planets. And so very often we try to stick to the ones for which we know the mass, because these are also the ones for which we got radial velocity data, and so good spectra to get good stellar abundances. So there's some sort of a bias here that we are mostly looking at the brightest planet hosts, and so Kepler is not a good case to do this kind of analysis in detail.
Yeah, but since over these two, like over the past a couple of years, and this kind of like small planets that have been kind of dozens already. Also, they also have relatively good mass and radius measurements. Yes. Also, I think also compiled by one of Revit's students as well. So because here for this distribution, you only need to plot the metallicity. So ranking, you will have that information as well. So it will be useful to check, see if such a distribution has been available or still limited to the data.
Yes, I agree. I will definitely check that. Yes, thank you.
Yes. And the second question for me is regarding the results in the later of your slides, showing the mass fraction in the planet and the mass fraction of iron in the star. So firstly, I would like to be clarified for your x-axis, the iron in the mass. So does that mean the iron, the fraction and mass fraction iron among all the elements heavier than helium, x-axis? Is that?
I'm not sure if I'm
Your
understanding.
definition. So what's the definition for F iron star? Can you remind me again? Yeah.
This one?
No, exactly the one you showed before. Yes,
one?
yeah, the x-axis here.
So F iron is the iron mass fraction in a rocky planet. So this is basically the ratio. I mean, Caroline can probably even complement this answer, but I think at least in this case, this is the iron over silicate. So iron core. I mean, if you think about a differentiated planet, is the core over mantle ratio, right? Or no, the core over total mass ratio.
Yeah, it's the exactly like the amount of iron over the total mass.
Yes.
I was looking at something else, so I was not aware of this question. But are you asking about the difference between these two plots?
I thought the x-axis it was the mass fraction iron among the or other elements heavier than helium, but now you tell me actually it's the mass of iron over the total mass of the star, right?
Of the planet.
So the x-axis.
No. So the x-axis.
Yeah.
Sorry,
yes.
This is the amount of iron over the amount of other refractories that would form.
Okay, that's exactly
also these building blocks. Yeah, so it's not.
So that's exactly what I expect. So in that case, and Nuno, also you mentioned that the distribution of this mass fraction in the planet and the star seem to have this sort of this correlation, but there's a little bit larger spread for the mass fraction in the planet. So, so to me, if we believe that our planets and star share the similar refractory material, I wouldn't be too surprised that they show this similar core mass fraction in terms of correlation here. But in terms of the larger spread for the mass fraction in the planet, I was wondering, is it because of the oxidation state differences for the planets even orbiting the same star? Because only considering the mass fraction in the star, you wouldn't consider anything difference in the oxidation state. But for the iron in the planet, consider mass and radius. So actually that has been influenced by oxidation difference based on the measurements, of course. So so that's why you can see such a little bit larger spread. So this is just my sort of like thought on this, but I'm not sure that makes sense or not. Yeah. So.
I think that's a very good question, and but an open question somehow. I honestly don't know exactly how we can expect how we can explain such a big difference in the spread. Maybe Caroline can give more insight than me, to be honest.
So it's a very good point, this oxidation state for these planets, and you see somewhat the difference or the effect of it when you compare these two plots. So on the left side, we just assumed all iron only to be present in the core, whereas on the other side, iron can also be in the mantle. So there is the effect of different oxidation states is illustrated by the difference between these two plots. So I think that it explains the spread to in partly, but there's also some aspects that are still not not clear. So
interesting.
It explains it to some extent. Exactly.
I do have some questions, but I leave someone else to ask first.
Are there other questions from other people? If I think Haiyang, you can also go ahead with your other question. I will have another input to this. You had anyway. I will make this input later. So please go ahead with your question.
Okay. In Nuno, in one of your slides, you show the Astrophysics 2019 data for photospheric abundance and meteoritic abundances. And I believe you also be aware that he published a new paper, I think this January or February or this April. So he showed another plot that photospheric abundances normalized to meteoritic abundances in terms of CI contracting abundances, then put as function of condensation temperature. And he seemed to claim that there's a positive correlation between the difference of photospheric and meteoritic with the condensation temperature, and argue that actually even for these refractory components, the CI contracting can be a good proxy for photospheric abundances. So have you been aware of that plot, or have you any comment on that?
Yes, I am aware. However, if I remember, okay, I've shown this plot because this was the motivation we had back then. But my impression is that these trends with condensation temperature, they are always very, very at the limit of the precision we really have in the abundance derivations. And so I think they are to be taken seriously, but with a grain of salt, So it's still under discussion. And for example, there were, in a slightly different context somehow, there were these works by Melendez and others who have suggested that there is a strong correlation between the condensation temperature and the planet. I even don't remember now exactly the details, but anyway,
solar twins.
Yes, for solar twins. And I'm personally a bit skeptical about it because I don't think that the precision we have in the measurement of the abundances is really enough to tell one from the other. And there's a lot of trends in these condensation temperatures that rise simply because of the galactic chemical evolution trends, So it's a tricky business. I prefer not to enter too much into it. To be very honest, since a couple of years that I'm not paying much attention to what's coming out from that, but it's really tricky.
Okay. Yeah. Okay. So actually, this leads to a very good question that I want to ask. Sorry, I have asked you. So, all of this we have done or show here is in terms like brighter stars. So, from your expertise or perspective, do you foresee any hair precision or relatively hair precision abundance measurements and for M stars?
Oh, I wish I could tell you yes.
Yeah,
I'm not sure. We are working on it, and many groups are actually working on it. And M dwarfs are tricky. I don't have here the plot, but I remember a plot by Barbara Rojas Ayala, who is one expert in M dwarf parameters, and she was showing the size, so the radius and the mass of a couple of M dwarfs as derived by different teams, and comparing that with the errors they put in their measurements, and things are completely off. And so it's really work in progress. I'm sure that at some point we'll be able to get good precise chemical composition for M dwarfs. For example, Vardani is using a machine learning approach now to try to tackle that by assuming that if the stars are from the same population as the FGKs we observe, then they should have the same chemical abundance ratios as well. So there's all sorts of approaches we're trying to explore for that, but it's a tricky thing. I cannot tell you when we'll be able to get abundances for M dwarfs with the same level of precision and reliability as we get now for FGKs.
Okay, so in that sense, we are more limited.
Sorry, so may I just shortly interrupt you? Nuno, do you still have time? Because we are already 5 minutes over time.
I can
because
stay.
you have another meeting.
Yes, I know. Yeah, I can stay for 10 more minutes.
Okay, perfect. Hayang, like there's another question by Joachim. Is your question, but I would just let Joachim ask his question and we can come back to yours. Is that fine?
Yeah,
it's okay. Yeah.
Yeah, I don't have a very technical question, but it concerns this unpublished paper that you referred to, and this alternative scenario for formation of Mercury, which I was quite fascinated, but I didn't understand at all. So I think it would be nice if you could just summarize a little bit what that formation scenario for Mercury is based on these iron lines, what you were referring to.
Okay, that's the question I was afraid of, because I don't really know the details of this model, to be honest. So I know that the idea is that you have rock lines, not only ice lines, you also have rock lines, regions of different, different chemical rocky species, they condensate, and these can actually produce, because of the different iron compounds, it can produce planets with different core to mantle ratios, depending on where they are formed. And again, maybe Caroline knows this in detail. To be honest, I don't know all the details of the model.
Okay, thanks.
Yeah, I think, yeah, maybe I'm also like this paper, I haven't read in such details, but we also have the idea, there is also the idea that when a planet forms, you have rock lines within the hill sphere as your forming planets is also hot, and so maybe an accreting, this is a bit linked to an idea that was put out from Anders Johansson for volatiles actually this year, and yeah, but I think this idea is not yet it's not laid out specifically to form supermercuries. So we are just I think in this paper we are trying to find some possible arguments how to form supermercuries, not by necessarily not by giant impacts. Yeah. Hayang, you still have your other question.
No, it's not asking. It's just actually a quick follow-up from Nuno just suggested for M stars. So actually, I just want to get a quick conclusion from you. So you think for getting the elemental abundances for M stars, so we are now more limited by the spectral measurements themselves, or actually by the atmospheric model for M stars?
My impression is that it's the model side. I mean, the model side overall. I mean, the spectrum of M dwarfs is very crowded with spectral lines, and this makes all the modeling complicated. But I mean, my hope now is with these new high resolution spectrographs in the near infrared. So in the near infrared, the spectra are much more nicer, smoother. You see individual lines, and you see the continuum most of all. And so I think this will allow us to go one step forward. And that's what many people are now trying to explore.
Okay, sounds promising. Yeah, thanks. Thanks a lot.
Thanks so much, Nuno. We are now like 10 minutes over time. I think as you have another meeting, I would close the seminar. Thanks so much. It was great to have you here. And some people already left, but I give you an applause from everybody. Thanks so much, and have a great day.
Thank you very much for the opportunity as well. It's good to present this and discuss. And if you have any questions, just drop me an email and we can continue discussions offline. Okay.
Perfect.
Thank you very much.
Thanks so much.
See you guys.
Okay.
Goodbye, everybody.
Bye-bye.